Welcome to this topic, which is mathematical modeling, and we are covering this topic for diploma in information and communication technology, that is DICT. The last topic in computational mathematics, and we shall be dealing with mathematical modeling. Welcome and get ready to learn. So before we venture into the main part of the lesson, we start with the definition, and what we shall cover is we have to understand that what is modeling first. Then after we understand what is modeling, the next step is to understand what is now mathematical modeling. And that's why when we say that mathematical modeling, we shall look at it in different perspective. What is it, why, and how? Then from there we shall look at the application, the objectives, the modeling cycle, and the principles of mathematical modeling. Then we shall look at the types of modeling that we have. So without much ado, let's direct move to what is modeling. And please remember to subscribe, and then remember to put some comments in our channel so that we can work on other areas that we have not covered very well. So we are here at modeling, and then what is to model? In simply, a model is just a replica of something happening in real life, and especially when you model something, is that you are trying to imitate something, or to show how that something appears. That's a normal modeling that most of us know. However, we shall look at it in perspective of mathematics. And as a model is a miniature or an abstract representation of something. When you present something, let's say a big, you can represent a lion with a small lion, which is a model, or an elephant with a small model elephant. Or you can represent a skyscraper with just a small group of a box showing that the replica of that, but just an imitation of what you are seeing. Yeah, it's simply a pattern of something to be made in a manner that you can have you can represent something in a manner that can be understood better. For example, you can also visualize something, meaning that you are trying to depict what you see in real life phenomenon or an happening. That's what we call a model. So there are so many types of modeling that we shall go through, but to model is simply to do a replica of something in real life, or an example of imitation or emulation in a real life situation, so that you can see how the object and the model they look like. Now we have physical modeling. We sometimes call it the prototype. These are something that you can see or touch. This mostly is like you are doing a model of something that can be touched, or something that you can uh, when you talk of types of modeling, these are we are going to see modeling types, which we are trying to look at them, and then we'll see that we have the following types of modeling, which we are talking of. The first one we are talking of the physical modeling, that is a prototype, something that you see or you can touch. That's why we say that it's just a constructed copy of the modeled object. E.g., you can have a model of an airplane, a model of a solar system, how the earth revolves around the sun, humanoid robot, you can have a robot that builds like a human, a building, a bridge. In this physical model is applicable mostly in thermodynamics, fluid mechanics, aeronautics, and architecture. When you advance in maths, you will see these the thermodynamics, the fluid mechanics, where you shall be trying to model specific physical modeling so that you can see and touch them, especially the one for can model the bridges, the building, the airplane. That's one of the types of modeling. Then the next part is modeling two. Is now number two is we are talking of schematic modeling. Schematic modeling, and when we talk of schematic modeling, we are saying that schematic modeling uh, is just a representation or a picture that represents something in a schematic, and that is simply a graph, something on a graph. Let's call it schematic. That's a graph, and then so is that it simply provide the meaning of visualizing a system structure, whereby it will give you the meaning of when you visualize something. So when you present something on a graph, it will give you that visualization, whereby you can come up with a model that visualizes some phenomena. That's why we say that schematic modeling provides means of visualizing. Yeah. For example, you can visualize an organization through when you are using organizational charts. You can see the top management, the hierarchy of the company, the management of a school, the hierarchy of a student leader. Then our process chart shall give you how the process follow. For example, you can look at the admission process. You'll have you get the letter, again you apply, you get the letter, you join. Just a process showing how things should happen. Then a graph, the graph, the graphs, the geographical maps, the diagram. Yeah, the vision information provided by the GPRS, we say GPS or GPRS, where we say we're talking about the vision information that we are provided by the GPS, that is global positioning system. That will show you it will show you a schematic diagram, whereby it can show you when you do some Google mapping, you'll see that they'll show you the diagrams, how the place look like. And this part of GPRS or GPS we shall cover more in our module 2, where I shall be dealing with the computer application 2, and we shall be dealing with the geographical position of our location in the earth. That is how that schematic modeling will cover. Then the next part is now the mathematical modeling that we are more concerned of, because this is now the area, because our topic is introduction to modeling, and it's a computational mathematics. So our area will mostly rely on mathematical modeling. And mathematical modeling is that representation of the behavior of real objects and phenomena in a mathematical language. Simply, you are just representing the phenomena and the real objects using the mathematical languages. It's just a mathematical modeling is just a form of mathematical language or languages. For example, here you see we have an algebraic equation which can be represented as x squared plus 2x plus 3 equals to 0. Then you can have differential equation where you say dx dy dx equals to sine x. Yeah. Then you have integral equation. We have algorithms. We have so many algorithms in mathematics, like the Ford-Fulkerson algorithms. We have so many Edmonds-Karp algorithm. We have so many algorithms. Then we have theorem. You know the theorem. We have Pythagoras theorem, the common one, and then we have formulas for quadratic equation, that is x equals to minus b plus or minus square root of b squared minus 4ac divided by a. Yeah, all this what you are seeing here, these are called mathematical modeling. Is just you are representing the behavior of real objects and phenomena in mathematical languages. For example, when you want to calculate to find the value of an x in an algebraic equation, you have to use a formula, and the formula is x equals to negative b plus minus. So that's how we are trying to present. We are trying to model that behavior of an happening or the phenomena in a mathematical way. That's what you call a mathematical modeling. And then why we do mathematical modeling? This is because it is indispensable part of the real world. That is, an abstract behavior of real world cannot be measured or quantified. So you have to model it so that it can be clearly understood. Then another reason is that technical, ecological, and economical and other systems investigated by modern sciences cannot be studied using regular theoretical method. Again, you have to model such systems for better understanding. Then direct experimentation is time consuming, expensive, dangerous, and simply impossible, meaning that there are some experiments you cannot do. You cannot do direct experiment. For example, you cannot take a real aeroplane and try to measure its uh, tension or any other by now draw ensuring that you do. There are some experiments you cannot measure or you cannot do them because they are dangerous and they can even cause a lot of harm. For example, you cannot test an aeroplane. Some experiments which cannot be done. So you have to look for a way, and that the best way is to now employ the modeling. Then, when you think of a real situation whereby it is dangerous to perform a direct experiment without a prior testing through computer stroke simulation, so it's now very good that you can do a real simulation so that in case what you are going to do is dangerous, you can just simulate it and see. And it is mostly applicable in computer, and that is simply mathematical model because the computer is just a branch of maths. That is also computational, that is computer modeling. E.g., when you think about launching a satellite, for example, you want to launch a satellite or you want to launch something related to space, you have to know that at what speed or velocity and what will be the trajectory and then consequences of that. So you have to do a model of that before you do a real launch. That's why we really need a mathematical modeling. Then where do we apply this modeling? Is it more it's applicable in which area? That's epidemiology, where we are study of epidemics, e.g. the one which is spreading at the moment, the corona. Then we are talking of biological transport. Then there's also a vehicular traffic, to know the traffic. Then optimal strategy in business, how to get the best way to do a business. Then in economics, when you talk of economy, it's also applicable. Then financial industry, and then engineering, and majored in software development, which is related to our area of study, which is a diploma in ICT or a ICT related field. We are to which is in future most of you will be focusing on software development. You can simulate a software before you do a real test in ground. Then the objective of the mathematical modeling is to the objective of it is to analyze, and then when you analyze the situation or phenomena, you have to make prediction. Then you have to provide insights for the real world phenomena. You have to provide insight. Then again, you have to find the optimum solution. You have to find the optimum solution for real world challenges. These are the languages of mathematics that modeling, which is a language that will solve to analyze the situation, make prediction, provide insight of the real world, and then do some giving us the optimum solution, the best solution for a certain real world challenge or a problem. Then when you talk of modeling cycle, you have to know that modeling cycle, there's steps to follow when you want to model. The first step is just you have to understand the real world. Understand the real world. That is cognitive activity. Understand the real world first. Then you have to conceptualize. You have to conceptualize world. Yeah, to come up with a representation. You assume that how will that scenario look like when you put in a conceptual world. Then you have to come up with now analyzation of modeling. You have to analyze the model. You have to perform analysis on the model to know that is it the best way you can conceptualize that. Then the next part is to do prediction, whereby you have to predict, where you have to predict. And when you talk about predicting, you have to know that when you predict now a certain outcome, you have again to interpret that outcome so that we can get now the results. And when you get the results, now you have to apply that results in real world. That's now the what we call the modeling cycle. Then let's talk of principles of modeling. First, in principle, we talk of the object. So the system you want to model, you have to understand the system you want to model. Then again, you have to look at what are the variables, the assumptions of the parameter you have to apply. Again, you have to look at the model prediction, what information the model gives. Yeah, when now you try to interpret the model, what information the model give, or how does the real world interpret the model? When you see the model, what is your outcome, or what can you get from the model? Then you check if the model is valid, and then meaning that when the model is valid, it means that that model is accepted. And when it's not valid, again you have to redo the process. Again you have to uh, go back to variables and then check again the parameters. Then you have to repeat the process until you get the valid model, and the valid model will be now depicting the real object in the ground. That is what the real the object will be depicting. Then from there, let's look at the types of modeling now in mathematics, and that is we shall cover three, that is statistical modeling, logical modeling, and model pseudo code. And even we have others that we shall cover on the way. So the first part, we are talking of statistical modeling, which is a body embodies a set of assumptions concerning the generation of some samples of data. When we talk of statistical, it's come from the word statistics. And you know the statistics are, we are talking of samples of data. We want to get some meaning. A population, you want to understand a population. So when you model a population, yeah, you have to model a population. You can model a population using probability distribution, and then you can model it using other statistical method of modeling. So a model is just a formal representation of the theory. So this statistical model, we will be representing the formal, representing the statistical methods of how that data can be interpreted. That's samples, and then you look of the samples of the population, their mean, you look over the averages, the mean, the averages. You have to look for so many things, their skewness, how they are skewed to one side or this other side. You have to know they're skewed on the left or skewed to the right. These are normal distribution. All these are, we say that all statistical hypothesis tests and all statistical estimates are derived from statistical model. Now from there, now you can now get that interpretation of that. When something is skewed to the right or skewed there, they give you a specific meaning. Then when you talk of now statistical model is also in symbol, in other definition, is just a pair of S and P, where S is a set of possible observation, e.g. sample space, and P is a set of probability distribution. You are getting a sample and then you see how the sample is distributed on a probability, meaning that you have to see, when you check a sample, see when you do you get some statistical data from that sample, find that we get what is the mean, what is first quarter, second quarter, skewness, kurtosis. Yeah, and then you get that it will show you the probability distribution. So what is the purpose of statistical modeling? One is for prediction, extraction of information, then distribution of stochastic structures, meaning that you're trying to get prediction. Yeah, you can predict when you get a sample of people, and then you see you can project that in the near future the rate at which the coronavirus is spreading will be reduced. You can now predict. And then you can again extract information. You can find that when what are the main causes of the spread. Yeah, you'll see, you'll get the information, and then you can also get the stochastic structure of the happenings. Then graphical representation of statistical data. Now you can now represent now statistical data in so many ways that you can use dot plots, where you use the dots to compare the frequency with different categories. Like I've seen here, you can see one, you can see again two. Those are just, you're using the dots, called the data. That's a sample of a dot plot. Then you know the bar graph. When you talk of the bar graph, the common bar graph, you have to know that's just a bar, a graph with bars. There's a bar graph, can show you that this year this is the amount we got, this year this amount we get here. Then you have a line graph, a line graph that is connected by lines. Have you seen, there's a one line, there's another one, then you connect the lines, put another, then there's another, can put it here, then you have to connect the line graph here. There's a line graph. Then circle graph, mostly we call it a pie chart. Call it pie chart, simply a pie chart, or a pie graph, simply a pie graph. Or a pie graph can have circle and then can give you percentages, can say percentages, and then yeah, there's a pie chart. That's where you're representing a statistical model. Then you have a histogram and frequency polygon. You can see that this is now the histogram. Yeah, there are so many other methods that you can represent the statistical model. Then again, we have to look at the spatial modeling. That is our spatial modeling. Is just analytical process conducted in conjunction with a GIS in order to describe a basic processes and the properties of a given set of spatial features. When we talk of spatial, we're talking of space features in the globe. We're talking of the globe, the features in the globe, the features in the globe. You want to know the features in the globe. This is the globe, so you want to know the features in the globe. So spatial modeling will give you as the features in the globe. Then the objective of spatial modeling is to simulate a spatial object. Is to simulate. It's not clear. Is to simulate the spatial object, meaning that any object in the space can be simulated, and then you can now get some more information about it. The another part is to facilitate problem solving in planning. So in planning, it will help you facilitate problem solving in planning when you want to plan something. In case for those are big projects whereby planning is needed, and due to different phenomena in the world, when you get that spatial modeling will give you the right projection of what you can do in a certain place. So it facilitates problem solving and planning. It can also help you to solve certain problems. For example, you know that in certain place you cannot come up with specific types of even types of buildings. You might be come across tsunamis and others. That's how it will help you in your planning. Then another part is this modeling is also essential in process of spatial analysis. We want to analyze the space, very essential. With use of modelings or spatial rules and procedures for analyzing the space, it will use specific models or spatial rules that will help you analyze the spatial data. That's now the geographical data should be using. So in other terms, spatial analysis or just spatial statistics, it includes the study of the formal techniques which study the entities using their topological, geometrics, or geographical properties. We call that spatial analysis. Then it includes variety of techniques that many states in their early development using different analytical approaches and applied in field as diverse as astronomy. When we talk of astronauts and that study and its study of the placement. So is that when you do spatial analysis, you are like trying to look at those techniques that can be employed in development of different analytical approaches as applied in the field of astronauts or astronomy. Yeah, the other part we are talking of now, the other part is now the symbolic modeling. We're talking of symbolic modeling is just a representation of entity of a system through a symbol, just symbol. Simply, symbolic can be mathematically or logically, meaning that you are representing something using symbols. So a symbol model is used whenever the reality is too complex. When something is too complex, you have to use a symbolic model, meaning that it's too abstract, can be portrayed through an iconic or analog model. The factor of the system variables can be represented by symbols that can be manipulated in a meaningful and fruitful way. So uh, you can use a symbol model to represent the reality of something. So modeling allows explanation. This type of model allows explanation, explanation, and extrapolation. Features of symbolic modeling, which you have to also know the features of symbolic modeling. It contains a lot of representation. Those are symbols. It processes and manipulates those representations based on a set of rules. There are rules you have to use, or there are programmed rules you have to follow, programmed rules. Then the rules operates on the representation according to their shapes. or syntax, and not according to what they represent. Yeah, you have to know that the rules applied only to their shapes or the syntax is not really what they represent, where in their semantics, the meaning. For example, when you say one, it represents one, and then we say one can be on, yeah, and then we say zero can be off, and then another zero represent that is a zero, a number. So it depends, especially in binary mathematics. So symbolic modeling has four stages, and you can find the stages. We say that there are five defined stages. First stage is entering the symbolic domain. That's the first stage. You enter the symbolic domain when you're doing symbolic modeling. The second one, developing symbolic perceptions. And the third one is modeling symbolic patterns. You have now to model symbolic patterns. Then encouraging transformation, whereby you are trying to see how the model will transform to the real interaction. Then maturity, or maturing the evolved landscape, meaning that now what you want to present, now that symbol will have those enough features to be to show that perception. Then we have talk of clean language techniques are used throughout to avoid contaminating or distorting the development. So during this symbolic modeling, you have to use, we call it clean language technique, whereby we do not allow distortion or contaminating the development or the metaphor landscape through the form, content, or presentation of the therapist question. So it means that during this process, you have to use what we call clean language technique. Those are to ensure that there's no distortion. Misunderstanding should not be there. That is symbolic modeling. So we are in this other part we call computer modeling, whereby mathematical modeling can get very complex, and so the mathematical modeling rule are often written into computer programs. Now that the mathematical rules, you try to make the computer understand them, and then make a computer to apply them. So we say that is called computer modeling. So that now we move to computer modeling. Example is now weather prediction, whereby we are using software to predict the world weather. Then we have economical models. We are predicting the interest in future, the rates of unemployment. Then we're also talking of a model of how large structures behaves under stress, like big bridges, like the one which is being constructed at the Mombasa. These are big bridges that now you see how they will react with the changes in environment, their tension, and live, their life, how long they can be used, 100 years, 200 years. That's how. Then mathematical modeling, we can also talk of the model pseudo code, whereby the pseudo code, the normal you have covered mostly in structured programming, whereby it's just an informal way of programming description, where you say that you will do this, then the next one I'll do this, and that's procedure. So we say that that's another way of we call it pseudo code modeling, because you are modeling something. At the end, you have to come out with a programming syntax that or you have to come up with a underlying technology consideration, whereby that what will come up with is the outcome of that pseudocode. You have now to interpret the pseudocode and then put the pseudocode in the codings of a specific language. Yeah, that's why it is useful for creating an outline or a rough draft of a program. That's how we do it. You have to come up with a pseudocode, then you come up with a program. Call that a model pseudocode. Then pseudocode summarizes the program flowchart. Yeah. Summarizes the program flowchart, but exclude underlying details. I will give you details. The details will be in the pseudocode. Then system designers, mostly the system designers, they write pseudocode to ensure that the programmers understand the software project. That's how they do. So pseudocode is just informal high-level description of an operating principle of a computer or other program. And you have to put it in a manner that it's just simple for anybody to understand, so that now the programmers can now convert that one to an algorithm. And then we talk of an algorithm is a procedure of solving a problem in terms of steps to be executed and in order which these steps are to be executed. An algorithm is merely a sequence of steps that you can take to solve a specific mathematical problem. Yeah, and then that can be regarded as a pseudocode. That how those steps. Then let's talk of logical models. Logical models, we have logical framework, then you have theory of change or programmatics. All these are called logical model. It's just a tool used by, let's say, used by managers to evaluate programs, to evaluate the effectiveness of a program. It's mostly applicable in business field. You can use during planning and implementation. That's where as a manager they use to know the resources required, the activity, the outcome of a program, what is the impact of that program. And there are so many ways that logical model can be presented. In underlying purposes of constructing a logical model is to assess if then causal relationship between the elements of a program. So there is a symbol here. We can talk of. We see that a logical model asks for components, that is input. This is the first component. What resources are going into the program, e.g., money, staff, equipment. Then activities. What are the activities we shall be doing? Yeah. So we see that e.g., development, material, training, what activity the program undertakes. Yeah. Then output, what is the produce or the product of that, e.g., booklets, produced, workshop held, people trained. Yeah. Trained people, that will now be the output. Then outcome shall be talking of outcome, the changes or the benefit that results from the program. Yeah. Increased skill, knowledge, confidence in doing a certain task. Yeah. That is how we think of that logical modeling. Activities, participant, then short term we have to know the long term, and the middle term. This is the middle term effect. Then it is easier to define work and measure it. That's the best advantage of logical model when you do logical model. Then let's talk of uses of logical model. You can use in program planning. You can plan, perform evaluation, especially organization assessment tools, strategic planning tools. You can talk of process improvement tool and process standardization tool. These are the uses of logical models. So I think we have reached the end, and this part is just an introduction part of modeling, and then we shall try to cover it in the next lectures depending on your reactions from the comment section. Thank you, and please subscribe and share Cal Academy. Then we shall be good to go.